Alright, welcome everybody to 2 o'clock class. So we're going to go over the image processing assignment today. I'm going to teach you everything you need to know for it. We're getting close to the end of the semester. It might not feel like it. We're like on week 12 or something. But basically, by now, you actually know all of the topics you need to know by the end of the semester. So the last 6 weeks of this class are just going to be practicing what you know. So the image processing assignment is going to be a good chance for you to exercise your artistic chops, to show your artistic creativity, and to impress me and earn some extra credit and stuff like that as well. The main technical skill for this assignment is working with 2D arrays, or technically 3D array in this case. And you'll see it's not really that bad. It's actually not, it's not hard at all. And I've taken some measures to make it easier on you all. So there will be more zybooks. Students in the previous class were asking, are we done with zybooks? And the answer is no. There's a zybooks chapter on sorting and a zybooks chapter on recursion that are both worth going over. And then after that, I'll see. So zybooks is actually infinite. So we'll see how far we go on zybooks. Because a lot of the topics in there are actually CSI 41 topics that we don't cover in this class. Some of them are still probably pretty useful, so we might get you a pretty good start on CSI 41. Like all the class stuff that you were doing, a lot of the zybooks was actually topics in CSI 41. So if you found them confusing, don't be alarmed. They're second semester computer science topics. If you learn them, then good. You got a good head start on CSI 41. First month of CSI 41 probably is on class design and getters and setters and things like that. Okay, so let's talk about image processing. First of all, groups have been assigned. So if you go into Canvas, and you go into the groups, you go into the people tab, you'll see that there is a group for image processing, and that'll tell you who your partner is. Contact them on Discord. If they don't respond by Friday, then let me know and I'll give you a new partner. Okay. So there are unfortunately a few students in this class that are AFK, and you don't want to be saddled with one of them. So if your partner doesn't respond, then the AFK people get grouped together, and they get to languish in obscurity on their own. So let's get going. At the end of last class, they asked me to make a rainbow version of Knuckles. Which is truly the pinnacle of artwork. I don't think any human being alive has made an image more beautiful or more elegant than this one. This moment in humanity is what all the various civilizations of the world, Greek, Chinese, Native American, is leading to this moment right here. The creation of Rainbow Knuckles, one of the most beautiful images ever made by mankind. So, it's not even a good rainbow, right? Like it's so ugly. Okay. So we'll maybe build on this. Okay. So we can only go down from here. Yeah, that's true. So the original image looked like this. And then I wrote a filter that made it look like this. Okay. So that is the before and after. And we can, in today's class, do the second person. So assuming the first person did filter 1, we're going to do filter 2. Okay. Is in the Louvre? Not yet. I'll begin negotiations soon with the Louvre. Let them and the Guggenheim and the Smithsonian compete for the... Okay, NFT. All right, so let's get on to the server, and I'm going to run you through the process of making an image from scratch. So we come in here into image processing, and a couple notes. First of all, main.cc, you pretty much don't need to touch. There's one thing you need to touch in main.cc, and that is putting in your name, what you did, your partner's name, what they did. And if you have a third partner, their name and what they did. Okay? So That's the only thing. You don't need to do anything else. I have a little note here. Nothing else below that you need to touch in main. Just put in your name so I know who your partners are and stuff like that. I was planning to work with 2 specific people, but was put into a group with someone else. Is there a way to resolve this? Yes. Like, message me. If any of you have specific requests for partners, like I said last time, you needed to message me by the start of class today, but it's fine. Just message me now, and I will place you with a group. Okay. So, yeah, so main, I wrote main for you guys. You don't need to touch main other than this part. And what main does is it uses something called the C-image library. The C-image library knows how to read and write image files. All the, maybe not every image format, but all the big ones. JPEG, PNG, GIF, you know, or GIF, depending on if you're a good person or not. So that does the hard work of like opening up the file, parsing it, getting the color data out, things like that. And then what happens is that once all that color data has been pulled out, it passes the image, which is held in a 3D vector. It's held in a 3D vector, and it passes it to filter 1. So student 1 writes filter 1. Filter 1's in a different file. And the reason why it's in a different file is because main.cc takes a long time to compile. It takes like 12 seconds to compile. And so I split them into different files so that we can get a faster compile time. And then the results of filter 1 get passed to filter 2. And the results of filter 2, if you have a third person, get passed to filter 3. And it writes the results each time. So here's main. We're inside of main right now. Let's go up to the top here. Main takes in command line parameters. This is maybe the first time you've seen command line parameters. What happens is you're going to run your program like a.out kyoto.jpg. So what happens is if you have these parameters here to main, it will set arg count, argc, to be how many words were on the command line when you hit return. So main space a.out space kyoto.jpg. So a.out is the first argument, and kyoto.jpg is the second argument. It actually tells you the name of your executable. And they're passed in an array of strings. And this is SeaWorld stuff. These are not what you would expect a C++ program to use, but that's actually part of the standard. Standard mandates that you're given a char star star, which is an array of char stars. A char star is how they did strings back in the SeaWorld days. And they're kind of garbage, but you don't have to worry about it too much because I've done it for you. So what happens is if the arg count is not 2, if they didn't type in a.out kyoto.jpg or whatever, then it prints a little message and quits saying, hey, this is how you run the program. If they did type it in, then the first, or element 1, the second parameter, element 1, gets passed to this thing here. This thing here takes in kyoto.jpg, opens the file, and puts it into an array, essentially. So you don't have to, so the C-image library handles all the hard work of opening it JPEG and saving a JPEG and stuff like that. You don't need to worry about any of that. I did all this code for you. At the end of the day, what happens is that my code calls your code. My code calls filter 1, passing in all of the image data, and then you just modify it. And it times how long it takes, and just in case you're curious, the timing data doesn't really matter. It's just in case you're curious. It'll tell you your code took this long to run. It'll take 0.02 seconds to run or something like that. And then the result of that gets passed to, it gets saved to disk. So it's going to save the results as filter1.jpg. And then it is going to pass the same vector into filter 2. So filter 2 is going to take the output of filter 1. And then when filter 2 finishes, it writes that to disk as well. And if you have a student 3, you're going to have to uncomment this because by default it's set up for 2 people. So if you have a third person, you need to delete this comment and that comment there. Open comment, close comment, delete those, and then it will write a third. It'll run the code with a third filter and then write filter 3 to disk. And you're going to upload all of the. You're going to upload your starting image, filter1.jpg, filter2.jpg, and if you have one, filter3.jpg to the Google Drive, and you're done. Okay. The big question is, how do I write an image filter? All right, so let's do it. Let's get into this. And we're going to build on top of the success of the 12 o'clock class. We're going to keep rainbow knuckles as our input, and we are going to so assume that some other person has done filter 1, and when you collaborate, you can oftentimes just send the files to each other. You know, you just email the files to each other or whatever, however you want. You can pass filter1.jpg, filter2.jpg to each other. You can share passwords, which I wouldn't recommend, but you could if you trusted the person. Like, I know there's a brother-sister team that is partnered up. They probably could share passwords. I don't know. How can one make that piece of magnificence better, though? See, that's I don't think you can. But I think we could work on the background, right? Somebody in the 12 o'clock session said we should just leave rainbow knuckles as is and just mess with the background of the image. Okay, but in order to get there, we're going to have to teach the 2 p.m. class how to make a filter. Okay, so we're going to be editing filter2.cc. Okay, and the reason why we're doing that is because the 12 o'clock class made filter1.cc. We're going to make filter 2, and so we're going to build on the success of the 12 o'clock class. And so here is where you're going to write your code. It's going to be in a function called filter2, and it takes in a 3D array. A 3D array. So if you've ever seen a picture before, which I hope you have, you should know that a picture is made of pixels. Right, a pixel is a little dot. If we were to zoom in on the masterpiece, if you zoom in far enough, you can see that this image is made of little dots, and each dot has 3 values there. It's got a red, a green, and a blue value. So if you've ever used like a color picker, has anyone here used a color picker before? If it was in Raid Shadow Legends, that's amazing. Has anyone here ever seen a color picker before? Some of these things. So you'll see that when you do a color picker, you can, no matter what you pick, the output is always going to be 3 numbers. It's going to be a red value. That's a pretty shade. I like that one. I'm going to write that one down. Painting the inside of my house with that. That's a good one. Okay. 55, 46, 94. I like that shade. It's beautiful. Okay. So, every color is an R value, a G value, and a B value. It's a red, a green, and a blue. And these values range from 0 to 255, at least the way that we're doing it. Sometimes, in some programs, they range from like 0 to 1, it's like 0.5. But we use unsigned chars. We use a number from 0 to 255. This is very standard in web development and things like that. The red value, the green value, and the blue value are held as 8-bit chars, essentially. So 000 is black, because that means there's no red, there's no green, there's no blue. If we did 25500, that's bright glowing red, because it is 100% red, no green, no blue. Obviously 02550 is bright green, 00255 is bright blue, 25500 is half red, half blue, so it's kind of looks almost purple or pink on this one. And then 255 is white. So what's really interesting about the white light that we're getting out of our monitor is that it's not white. We're actually not seeing white light right now. We are seeing a bunch of red and a bunch of green and a bunch of blue. So if you got really close to your monitor, you would not see white light. Okay, you would see a bunch of red dots and a bunch of green dots and a bunch of blue dots. And what happens is that when they mix together, your brain interprets them as white. There is actually no such thing as white light in and of itself. Like, white light is a mixture of different lights, you know. So yellow is not really there. Yeah. So if you were to look at yellow, it's going to be red and green, and very little blue, or no blue if we want. Okay. Yellow. There is yellow light in the real world. In fact, sunlight, is yellowish, right? It's a spectrum. There's photons that have different wavelengths, and there is a spectrum of light that we perceive as yellow. Now, here's the thing: the light coming out of your monitor is not yellow. There is such a thing as yellow light, but that is not actually what's happening. That is not what we're seeing right now. What we are seeing right now is a bunch of red and a bunch of green. So it's like somebody is shining a red flashlight and a green flashlight in your eyes, and your brain's like, it's yellow, I'm seeing a yellow flashlight. But it's not. Somebody could shine a yellow flashlight in your eyes, but from a computer monitor, it can't. Computer monitors cannot make yellow light. They make red and green. Okay. So, it's an illusion. It's an optical illusion, and that has to do with how the human eye works. So there is 3 different types of light receptors in the normal human eye. Okay. And one of the receptors perceives red, one perceives green, one perceives blue. And that's why our monitors produce red, green, and blue. Because those are the 3 things we're sensitive to. And what happens is when we see yellow light, then the receptor for green and for red activate at the same time. And based on the ratio of red activation to green activation, our brain goes, oh, I must be seeing yellow light right now. So what computer monitors do is they produce this much red and this much green, which activates the red receptor and the green receptor, and your eye goes, oh, report it to the brain, I'm seeing this much red and green. And the brain's like, it must be yellow then. And so we're actually perceiving something that is wrong. We are actually not having yellow light incident on our eyes. It's all a giant conspiracy by Big Monitor to make us see colors that aren't there. So, yeah, but because these are the 3 things that our eyes see, if a monitor produces red, green, and blue, then it can reproduce any natural light. Natural light comes in a variety of wavelengths. The light coming out of your monitor comes in 3 wavelengths: red, green, and blue. And just by varying the intensities of them, then it can simulate different colors. All the colors, in fact, if you had enough precision. Now, nowadays, 10-bit color is kind of coming online. 8-bit color is kind of not quite good enough. But for this assignment, we're going to be working with what's called 8-bit color. So 8-bit color means that each value ranges from 0 to 255. And so what you're going to have is you're going to have a 2D image like this. And every point on that 2D image, for every row, by the way, the top row is 0. So whenever you do images, the top row is 0, the bottom row is whatever the max is, and the leftmost column is 0, and the rightmost column is the max. So 0, 0 in image space is always the top left corner of the screen. Unless you're working with OpenGL and using uniform coordinate systems, which case 0, 0 is the middle. But for all the stuff we're doing, row 0, column 0 is the top left corner. And as you increase the row, it goes downwards. Okay. Someone call Alex Jones, yeah. Did you know it's not even yellow light coming out of the monitors? Yeah. My CSI 26 people made an Alex Jones quote generator. So you'd probably train it to rant about yellow light or something. So yeah, the reason why we're passing in a 3D array is because we've got a bunch of rows of pixels, a bunch of columns, and then at every pixel, at every point on here, it's got a red value, a green value, and a blue value. So that's the 3rd dimension. The 3rd dimension is color. Row, column, and then down is color. Okay? I don't believe so. CMYK is used for printing. CMYK is very commonly used for printing. And the reason why they use CMYK for printing is because monitors emit light. They do what's called additive light. So if you do red and you do green, then they add together and you see yellow. Printers work on subtractive processes. So if I had a red paint surface and I shined blue light on it, no blue light would be reflected because it only reflects red light. That's why it's red. It reflects red light only. So if you shined a green flashlight on it or a blue flashlight on it, no light would get reflected. Okay? So CMYK are the complements of RGB. So C, if you print C, it absorbs everything but C. If you put M on there, it absorbs everything but M. And so black absorbs all light, right? So that's why paper is always white by default, unless you're doing some yellow construction paper. So, you know, paper starts as white, and then as you add ink to it, it reflects less and less light. So that's why it is that way. We don't use black paper with white ink, you know, or something like that. It'd be very hard to do. Okay. All right. But yeah, the CMYK is just the complement of RGB. And hue saturation and what is it? Hue saturation. Herpes. No. All right, I'm gonna have to search for STD. Dang it! I'm still not getting anything about C++. Hue saturation. All right. Vividness, value, hue saturation, value. Okay. Yeah. So amusing. Okay. So what we're passing to our program is a 3D vector. For every row, for every column, there are 3 planes. The top plane is red, the next plane is green, and the next plane is blue. All right, so how do we use this? Filter 2 is interesting. Let's get rid of this demo code. Oh, we already have demo code here. All right, let's just comment this whole thing out. And let's make our own. So your for loop is going to be okay. So your for loop is going to look basically like this. So for every row, for every column, we're going to do something. And if you don't do anything, then it'll just not change the image, and you'll just have your original image. So let's say we wanted to do grayscale. Okay. So we can get the red value of the red value of the current pixel by doing this. We can say vector.at_row.at_column.at red. I made a little constant here. So red is the top plane, green is the next plane down, blue is the next plane down. So this will give me the red value at the current row at the current column. And I can do the same for G and B. Okay, and then if I wanted to grayscale something, you grayscale something by averaging the RGB values together. So if I said int average is equal to R plus G plus B divided by 3, would this successfully average the red, the green, and the blue together? What do you think? That is correct. Please excuse my dear Aunt Sally. Can't do that. Got to do that. Okay, so now, now we know the average of the red, the green, the blue. So how do we set? Because what we're going to do is we're going to set the red to the average, the green to the average, and the blue to the average. If we make the red, the green, and the blue the same, it's always going to be a black or white or gray, right? Right. 100, 100, 100 is gray. 200, 200, 200 is gray. So how do we set the red, the green, and the blue at this point to be equal to the average? Anyone want to take a crack at that? Give you a hint, the code to read and write to the vectors right there. Could you repeat the question? Yes. So we have gotten, at the current point, we have gotten the red value. We've gotten the green value, we've gotten the blue value, and we've averaged them together. How do we set the red value to this average? How do we set the green value to this average? How do we set the blue value to this average? If we set R, it's not going to actually change the vector, because what we have here is a vector that is passed by reference. So we need to actually modify the vector itself and change the red value at the current point to be equal to the average. So what we need to say is very good. We say vector I, j, red is equal to average. Or you can use .at, either way. Just like that. If we set them all to average, they turn the same color. Well, if you have the red, the green, and the blue the same color, it's grayscale. So we average the red, the green, and the blue together to get the average brightness of the pixel. And then we set the red, the green, and the blue channels each to the average. It will turn black and white. Grayscale. So now that we've got our filter here, we save it. We type make to build it. Make, not compile, make. There's going to be people on the help center at midnight the night before who haven't started, who haven't watched this lecture. They're like, I'm trying to compile it, it's not working yet. You have to type make. And what you'll see is the first time you build it, here, let's do a first time build. The first time you build it, it's going to take a while. You'll see that main.cc takes a long time to compile. And the reason for that is because the C image library is like 100,000 lines of code that it has to parse. And it's not small and dainty. It is a large library, and it does all the code in one file. It's got to parse and use the whole thing. So you can see main took a long time, but then filter 1, filter 2, filter 3, those got compiled really quickly. And so the next time you modify your code, I'll just do nothing. You type make again. Look, it only recompiles filter 2. It knows that was the only file that changed. So rather than doing a full recompilation every time, it is only going to recompile the files that changed, which is much, much faster. It greatly improves your workflow, because nobody wants to sit around waiting for 12 seconds for your code to compile. That's how it used to be, by the way. When I first made this assignment, everything was in main, and then every time the students made even a little change, they had to wait 12 seconds for it to compile, and then they could run it. And it annoyed me. And so it annoyed me enough that I split the assignment into having the C image code in main, and your code in filter 1 and filter 2 and filter 3. And main calls the functions over there. And these functions don't know anything about CImage. All they're handed is a vector of integers. And they can just mess with that vector of integers however they want. And then the CImage code over here reads the file, writes the file, blah, blah, blah. But through that, because I separated the interface like that, every time you modify the file, it takes like, a third of a second to come out instead of 12 seconds. Yeah. So, okay, so we've compiled our code. So step 1, write your filter. Step 2, compile it using make. Step 3, well, we first need to find an image, but fortunately we have an image. We've got the Knuckles image from the previous class, but normally we'd upload that. But let me show you how to do that again, just in case you forgot. So you have to find your own starting image for this assignment. I'm not giving you one. You have to find one. And you have to find one that works well for your assignment. Like if you're going to be doing an image, a grayscale image filter, don't start with a grayscale image, because it won't demonstrate your code working. So you have to find this nice match and synergy between your starting image and the code you're writing. Okay. This is one from the first class that I taught. Stand among the ashes of a trillion dead souls and ask the ghosts of honor matters. So, yeah. So you can find something like that, and so I'll just save the image to show you how the process works. So you find a meme, I'm going to save it to my desktop. Close out. And you don't have to do this every time. Only the first time you have to upload the image. After it's been uploaded, it's uploaded. You don't have to repeat yourself over and over again. So you go to WinSCP. If you don't have a Windows machine, any SCP client will do. And you log in using your username, host, password, etc., etc. And when it launches, it'll show you your computer on the left-hand side and the your server directory on the right-hand side. This is how you connect your home computer to the school server. And I'm just going to drag over honor.png like that. And it is uploaded. And if I type ls now, there it is. There's the file that I just made. If I ascii it, you can see, yep, that's it, all right. Low res, but good enough to recognize it, right? So now if we run the program, so we type to make, the next thing to do is to type a.out to run it. But you can't just type a.out. You have to give it a command line parameter. You have to tell it a.out honor or whatever, right? Like that. Then when you do that, it runs the image filters on honor.png. It loads it from disk, it runs the filter on it, saves filter1.jpg, runs filter2 on it, saves filter2.jpg, and is done. So if we come back in here into WinSCP, we can look at the results of each stage. And so we could right-click and choose Open on filter 1 and see that it looks quite horrible. This would be a very low artistic score, right? And then we can run it on filter 2. We can right-click, choose Open. Don't double-click. If you double-click, it opens it in a text editor. I don't know why, but it does. So rather than double-clicking it, you right-click and choose Open. You guys all see that? So you run your program, and then you right-click and choose Open. And what you'll see is that it is now, the original image plus the rainbow filter plus grayscale. All right, so you can still see the artifacts from filter 1 here, but everything's been grayscaled. Okay. So no deep fried memes, no modern art that looks horrible, and you're like, but I want it to look horrible. No, sorry. For this assignment, you're graded on artistic sensibilities, and my artistic sensibilities are not to do stuff like this. This, to me, indicates a mistake was made, and I don't allow you to play it off as a deliberate thing. Now, that said, mistakes are great on this assignment. How do you see filter 2 in the image alone? You can't. Filter 2 takes filter 1 as input. If you just want to see filter 2 alone, then you could comment out, I guess. You can comment out filter 1. That floats your vote. Art is like subjective, man. It is. And in the previous class, I had a couple bugs, some deliberate, some accidental, and they actually ended up looking really good. So this is actually a great assignment to screw up on. There's all sorts of interesting bugs that result in very interesting image filters. So if we run this again on Honor, now you'd see filter 1 takes no time because it's commented out. And if we right-click and choose Open Filter 2, then you'd see filter 1 did not run. Okay. So I'll put it back in Vim, or whatever. I'll leave it up for now. And then if we run the program on Knuckles, was it Dewey? Do you know Dewey? Then filter 1, if we look at it, is going to be unmodified, right? Because we're not doing filter 1 got commented out, so it's just the same image. And then filter 2 is going to be a grayscale version of it. Okay. So how do you run your partner's filters? Your partner sends you their code, and you put it in for filter 1 or filter 2 or whichever one they are. They can just send it. They can SCP it over to you. They can SCP it off their the server just as easily as the SCP files to from. They can do this. They can drag filter 2 over, and then they can send it to you on Discord or something, and you can copy it over that way. Easy. It's just like an RPG 40. Yeah, kind of. You don't, except for this one, you don't need to collaborate on the same file because you're working on different files. And so there's more of a separation You know, you're just kind of doing your thing in filter 2 or filter 1, whichever one you are, and they're doing their thing. And then when you got an interesting result, then you send it over to them and they put it in and see how they work together. Okay. So you'll be grading one of the partners. I'm grading the final product. So on the final product, you're going to upload the original image plus filter 1, the original image plus filter 1 plus filter 2, the original image plus filter 1 plus filter 2 plus filter 3 if you've got 3 people in your group. So you're going to upload either 3 or 4 different images to the Google Drive. They must stack on top of each other. It's not 2 different people just doing their own thing. No, you have to work with one another. This is the point of partnered assignments, is to teach computer science students the hardest thing in computer science, which is social skills. To learn how to work with another person, because friendship is magic or something. I don't know. The reality of computer science as a discipline is that we're actually extremely social. The stereotype of programmers is that we just sit in a dark room and play Minecraft all day and don't talk to people. But the reality is, when you work in the real world as a programmer, you're constantly talking to people, and you have to learn to work with people. You're going to be on a team of 5 other programmers, you know. Or if you are the only programmer in a company, which I've been before, that everybody talks to you because they're like, hey, I need this done by tomorrow. And you're like, all right, could you lay out for me exactly what you need, and I'll see what I can do, you know. And if you piss them off, you're like, no, I can't do it. Sorry, get out of here, burn in hell. Then, your career isn't going to go very far. You know what I mean? You got to learn how to stand up for yourself and stuff. But, you have to be able to talk to people and work with people. And so for this homework assignment, you cannot just be like, I'm going to do filter 1, you do filter 2, and we're just going to submit the original plus filter 1 and the original plus filter 2. Nope. They have to, filter 2 takes as input the result of filter 1. Okay? So, remote works means I have to type to team members. Yeah. Do you use Slack, Bill? What do you guys use? Microsoft Teams, Slack, Discord? What's your collaboration tool of choice? Slack, Zoom calls. Mm-hmm. Pretty standard. When I watch my friends in Silicon Valley coding, they usually just have their Slack channel up on the side of the screen. They're doing their coding, and then people are going, bloop, bloop, bloop. Hey, has anyone thought about what happens if they put in a negative? Oh, no, I didn't think about it. I'll do it right now. And they're just constantly talking to people, You can't... in this class, I've had groups melt down before because the 2 people just couldn't get along, and I don't know. There's probably some educational value in that or something. I don't know. So, Discord. Yeah, it was Discord. Some of those groups definitely devolved into Discord. Most definitely. Okay. I've always thought that Discord was named after the dragon from My Little Pony. All right. So let's build on our work here. All right. So vim main.cc. Let's put filter 1 back in here. Vim filter 2.cc. So do you guys understand what's going on here? Like at this row, at this column, the green value, that's the red value. We're getting the red value at that column, at that row. We're getting the green value at that column, at that row. We're getting the blue value at that column, at that row. And you don't have to just do something simple like this. In fact, this would be a fairly low difficulty assignment. Last time I showed you, you just increase the relative color balance. But there's a lot of things you can do. Like you can put if statements in. Like, check it out. If I were to say, let's say I only wanted to grayscale Knuckles. Knuckles is pretty red. You know what I mean? Knuckles is pretty red. So what I could do is put an if statement in and say something like this, like if the red value is over 150 and the green value is below 150 because I don't want to grayscale the grass, because white is high red and high green, So I'm going to say if the red value is over 150 and the grass is under 150, which I guess I did this last class, so it's not a guess now, but it was a guess back then. I just guessed these values. Then set it to be grayscale. So what I'm trying to do here is kind of just only change Knuckles to be grayscale and leave the grass and everything else alone. Okay. So if I do this, Yeah, I'm gonna cancel out filter 1 again, actually. Okay. Look at that compile time. And I did pre-compiled headers, which reduced the compile time by a few seconds, but one of the great takeaway points from computer science is that when things annoy you by being slow, that's when computer science people get motivated to make it faster. And so as long as you don't touch main, you don't have to go through this slow compilation process every time. So if we run this on a.out on do away, then check it out. So I put an if statement that said if the red value is over 150 and the green value is below 150, grayscale. So all the white, well, it's still grayscale, I guess, but you can see this yellow area here probably had enough gray in it, or green in it, that it didn't get grayscaled. Do you guys see that? It's pretty cool, right? Like that's, a couple lines of code, and it's a pretty cool effect. So Knuckles is now gray instead of red, right? Why is the edge still visibly red? Great question. That was not intended by me. I didn't know that would happen. And you remember how I was saying in this assignment, bugs are actually pretty cool a lot of times, and this is a bug. And the reason why it's a bug is because I think at JPEG creates artifacts. You see the JPEG artifacts here? It's because it uses something called a discrete cosine transform that grabs blocks of pixels and does like a cosine on it. And so you can see the ringing effect. Anytime there's a big discontinuity, the cosine tries to approximate it. And the lower the JPEG quality, the more ringing you get around the edges on it, like this. What's probably happening here is that it's getting blurred between the green of the grass and the red of Knuckles. And so I think these points here had enough green in them that it went over the threshold, right? So it needs more JPEG, yeah. Discrete cosine transform, yeah, DCT, discrete cosine transform, is what JPEG does. JPEG is not a great compression algorithm. We use it because it's common, but anytime there's an edge or discontinuity like this, it just gives garbage results, especially at lower quality settings. So there was enough green in it that it didn't grayscale, and so we ended up with this kind of cool red line here. So it actually looks pretty neat, right? Do you guys see this? Like this is a bug that actually resulted in a pretty cool output. His body turned red, but his face and eyes did not. And we got this cool little red outline here. And so you could turn, something like that in. You're like, yeah, look, I wrote an image filter that grayscaled just the body, but I left the edge as red and left the eyes untouched. And that would be, and everyone would be like, oh, very good, very good. And you're thinking to yourself like, oh, it was a bug. I screwed it up, but in image processing, a lot of times the bugs actually look really cool. And so you just kind of work with it, Would it be possible to turn the border blue? Probably. Using an if statement, you could probably try to isolate the blue, the red line, and turn it blue. In areas that have a lot of red, you'd have to be careful, because if you say it has a lot of red and a lot of green, then it's going to pick up the white, because white is red, green, and blue. So you'd have to kind of be very careful with your if statement. Yeah, you could probably turn that blue if you wanted. Or we could try changing the background to be grayscale. So let's go through the workflow again. So this is the workflow you're going to be in for this assignment. So once you got your image loaded up and everything, here's the workflow. Step 1, edit the file. And make whatever change you're going to make. In this case, I'm going to not it. So I'm going to say grayscale everything but Knuckles. I'm going to try this. See how that works. Saving, quit. So step 1, edit the file. Step 2, make. Step 3, run. And step 4, go into WinSCP, right click and choose open. Really? Strange. There we go. And so that grayscaled everything that wasn't the bright red color. Right? And so you can see the grass is now grayscaled. And the eyes, the mouth is no longer yellow, right? It got grayscaled also. So The edge isn't visible because the edge turned grayscale as well, but you can see there's like a black edge on it now. So, what do you think? Kind of cool, right? Sky's the limit. If you want to sepia tone something, I got code for sepia toning in filter1.cc right here. You can't, by the way, you can't just like use my code. You're like, all right, for my assignment, I'm going to sepia tone. Uncomment. There you go. No, 0 difficulty. No points. Okay. So you can't just like turn in my code to me, all right? Yeah. So it's not grayscale. This is rainbow. So I've got demo code in the filter assignment. This just adjusts the relative color values. This one here is sepia toning, so it sets the red value equal to the red value times 0.393 plus the green value times 769 plus the blue value. So there's just these magic numbers I found on the internet. And if you know what sepia toning is, it looks like this. So it creates kind of an old school look, old timey look. Thanks. And that's a vignette effect there. So you see that vignette where the corners are darkened. So we can do vignette on it. Put filter 1 back in. So, all this code. So filter 2 has vignette code in it. So the vignette code darkens the corners. So hypot is the Pythagorean theorem. So it gets our current, here we go, hypot. So it gets our current row, yeah, and sees how many rows we are from the center. The center is rows divided by 2, right? Gets our current column, sees how far we are from columns divided by 2. And so this is the distance we are from the center. This is the maximum distance across the entire image. And then we use a little bit of algebra like this to determine the brightness that it should be. So at the corners, it'll be 0 brightness. In the middle, it'll be 100% brightness. And then for every spot in the vector, for every spot, for every column, for every row, for every color, R, G, and B, then it gets adjusted by the brightness. So the corners will be darkened down to 0. The red gets set to 0. Green gets set to 0. The blue gets set to 0. In the center, brightness is 1. So the red, the green, the blue are left untouched. And so as it goes from the center to the corners, they will progressively darken. You get a cool little vignette effect. So make... And again, you can't just turn my code in. So you're like, I made vignette. No. The rainbow code looks scary. Yeah. Yeah, that was 10 minutes of coding right at the end of the last class. Like, add a rainbow to his body. And I was sitting there, like, scratching my head, like, I'll do this. In and out, delay. And so if we want to see the results of the filters, the first filter's result is in filter 1. We can see we added a rainbow effect to it. And then filter 2, we open that, and you can see that we added a vignette effect. So the corners are darkened now. The center is brightened. The corners are darkened. So even more beautiful than before. If we ran this with honor, if you don't type in the right name, it throws an exception. You probably fix that actually. Yeah. D5. D4D. Put it all the way down here. GG equals capital G. That's probably why I didn't do it. Okay, so I wrap this whole thing in a try block. So if this thing throws an exception, which it will do if it can't open the file, then it jumps down here, catches the exception, prints error opening file, quits. So, here we go. Any questions? Alt's compiling. Any particular filter you'd like to see? So now if I try opening a file that doesn't exist, it'll print error opening file. At least tell you now. Okay. Image over another image. Yeah, you could do that. Yeah, it's doable. In fact, we should go over the README actually. So the README mentions a couple things you have to do in order to get 100%. One of which is you have to add a watermark to your code. And I was kind of expecting you to do that manually by drawing directly onto the image. But you can actually composite another image on top of an image. I can show you how to do that. And then you have to add a secret message. So usually it's like hashtag, go Bruins or something, I don't know. So that's part of your assignment is you have to write directly onto the image. And the good news is in filter1.cc, you do not have this function, but I wrote it in the previous class and I'll upload an explanation of it. Is that you can pass in your image to a function like this and pass in minimum and maximum x and y. I just made this function in the previous class. It doesn't exist until now. But here it is. You can just copy it and use it. It's fine. And so starting at the minimum y, going to the maximum y, starting at the minimum x, going to the maximum x, set the red, green, and blue to 0. So what this is going to do, it's going to draw a black box between minimum, maximum x, minimum, maximum y. So if you pass in 50, 50, 100, 100, then it will draw a box from pixel 50 to pixel 100, a square on there. Okay. And so right here in filter 1, we're calling it a couple times. This draws a couple of vertical slashes, like you'll see on here, like that. Vertical slash, vertical slash. Okay. That actually turned out pretty well. Look at that. So we added a rainbow effect to the crayfish, and the area down here is all grayscaled, and I mean, this looks horrible, but it worked out all right, I think. I don't know. It's not bad. And you can see there's a couple black lines here. So would image on image be the extra blood on the sea serpent example? It could be, or they could have increased the intensity of the red, is another thing they could have done. Now, in years past, students had to worry about overflow and underflow. I actually decided to take pity on you for this year, and I modified it so that you're actually given a vector of ints instead. And so the color values range from 0 to 255, right? Ints can go from negative 2 billion to positive 2 billion. So what happened before was that if you tried setting the red value to like 260, it would overflow and become 5. And so what I'm doing instead for you guys, just because I like you, if the red value goes from 255 to 260, when it goes to save it to disk, it actually lowers it to 255. So it does what's called saturating arithmetic. So inside of main.cc, when I go to write out your image, I go through your whole image, and if any value is above 255, I set it to 255. Because the image that gets written out uses unsigned chars. Values is 0 to 255. But what I give you is a vector of vectors of ints. And so if you have 300 or 500 or 1,000 in there, as long as you don't go above 2 billion, you won't overflow. It's a lot harder to overflow now. And if you underflow down to negative 100, well, it'll become 0. So if you try outputting a color of negative 100, negative 100, negative 100, it'll output black. 0, 0, 0. Okay? That makes sense? So we are doing saturation, or I'm doing saturation for you. So if you exceed, and the reason why was because before students were like, brighten an image, right? So we could write an image brightener really easy, right? We could come in here and say for every row, for every column, vector dot at I dot at j dot at red times equals 2, right? So this would double the intensity of each of the pixels. Okay. And what would happen though is that if you had 200 before, 200 would double to 400, which would overflow and wrap around to 145. So it actually darken the red part. But let's say the green part of the blue part went up. So that's what would cause the deep fried effect, is that the red value would go down, the green and the blue would go up, and it would change colors rather than brightening. So what I'm doing now is I'm saturating it. So what will happen if you keep doubling the values, it'll get brighter and brighter and brighter, and then it'll eventually just turn white, which is correct. Saturating arithmetic is correct when doing image processing. It's not correct when like doing algebra or something like that, because you want it to overflow. You want it to underflow if you're doing algebra, because if you have like 255 and you add 10 to it, it wraps around and becomes 10. And if you subtract 10 from it, it underflows and becomes 255. So 255 plus 10 minus 10 is 255 with normal. That's why numbers overflow and underflow, so that algebra works. With saturating arithmetic, that doesn't work. That doesn't hold anymore. If you take 255 and add 10 to it, it's still 255. And if you subtract 10, it's now 245. So we don't do saturating arithmetic usually anywhere outside of, you know, signal processing and stuff like that. So now that we've added a lightening filter, we can see the result of the first filter now. See, it's much brighter now. You see that? It doubled the brightness of every pixel. And then the second filter, which is doing the vignette. What happened here? I opened the wrong file. I must have. Yeah. Okay. And then you can see the vignette on the corners there. So that is, and it brightens the center and it darkens the corners actually. So the center is even doubled again. So you can see it's starting to, it starts just turning into white when you brighten it too much. But it's really nice when you do saturating arithmetic. That's kind of what you want. You just keep brightening it and brightening it and brightening it, and it just turns eventually white. It's fine. The deep fried overflow look is not a great look. Okay, so if we do this with the honor image, oops, not you. Let's see here. So you can see it looks terrible now. It's great. Looks like a bowl of. Looks like a bowl of ice cream now. So it brightened enough that it triggered the rainbow filter a little bit more. And so it added a rainbow effect to the pile of crawfish. But when it brightened it lost enough of the detail. And the vignette in the middle there doubled the values again. So you can't even tell what this was originally. It just looks like a pile of ice cream. It's great. It's great. All right. So, if we wanted to composite two images together, yeah, let's do that. We got 7 minutes. The previous class gave me like 10 minutes to do the rainbow filter. The rainbow filter, by the way, I guess I should explain it at least a little bit. Is that it uses how far you are away from the left edge. So the left edge is 0, column 0, and then we use I, which is, I guess, columns. It seems backwards, so we call it rows here. Huh. I don't know. But we're going to use the distance from the left edge. And then I just kind of eyeballed some trig. So this increases the wavelength by 20 times. Because cosine takes radians, and so like every 6 pixels it would cycle through the whole thing. So what I did was I divided by 20, so every 120 pixels it'll go through one cycle. And then it'll range from positive 128 to negative 128. So it'll add to the red and it'll decrease from the red. And then I did the same for the sine and the cosine. This one had a little bit of phase offset. These have different wavelengths. And so all of them are going to be adding and subtracting to the red and the green and the blue channels separately. And I was just trying to eyeball a rainbow effect, and it turned out absolutely horribly, but memorably. Because remember, bugs on this assignment are happy little accidents, like Bob Ross says, right? You just try stuff, see what happens, and at a certain point, I would just start like messing with these values, you know, and maybe I'd make an animated GIF out of it, you know, because you can do that in CImage, and so maybe have the rainbow pattern moving across Knuckles or the shrimp or something like that. Okay, so let's do compositing. Let's do compositing. Vim filter 3.cc. Let's do this one maybe. So we'll take in 2 vectors. Visual mode, Y to yank, P to paste. We're gonna have vec and vec 2. Okay, and so we can only composite things where both images exist. So the number of rows, the number of columns, the number of colors, we're going to take as the minimum of the 2 of them. So vector.size greater than vector2.size, if then vector size, otherwise vector2.size. Okay, so what I'm saying here is that if vector1.size is bigger than vector2.size, that needs to be so whichever one has, oh no, that's the bigger one. We need the opposite, don't we? We need the opposite. Whichever one is smaller, right? Because if you have a 10 by 10 image and a 100 by 100 image, you can only composite them in the 10 by 10 zone. You know what I mean? Without going out of bounds. And I guess we can move around the location or something, but we got 4 minutes, so you know, forgive me on this. On the previous class, I showed how to. I did a blur filter. You probably should watch the video from the previous class because I talked about different stuff. But I did a blurring filter, and I blurred by getting the red, the green, the blue values from the people above me, below me, left of me, right of me, and setting my red value equal to the average of the 4 neighbors, my green value equal to the average of the 4 neighbors, the blue value equal to the 4 neighbors. And normally when you go up a row or down a row, you can go out of bounds, right? Because if you're on row 0 and you go up 1, you're out of bounds. And if you're on column 0 and you go left 1, you're out of bounds. So what I did was I just modified the for loop so that I would start on row 1. So I just didn't blur the outer edge of the image. That way it simplified my code. I didn't have to do crazy bounds checking on it. So I'm going to do the same thing here. I'm just not going to worry about bounds checking by just taking the smaller of the 2 dimensions. So if we have a 10 by 20 and a 20 by 10, it'll only composite the 10 by 10 area in the middle. Okay, so columns, vector size is less than vector2 dot at 0 dot size, then question mark. So whichever one's smaller is the one we're going to use. 0 dot size. Otherwise, vector2 dot at 0 dot size. I don't want to waste time bounds checking right now. And the number of colors should be the same for both, so I'm not going to worry about that. Okay, so oops. Okay, so this code composites vector 2 on top of vec. So it's going to take all the data and just average them together by averaging pixel data together. So vec.at I dot at j dot at red. So the red value is going to be the average of vector 1's red value and vector 2's red value. And we're going to do the same for green, same for blue. Does that make sense? So we're just going to take the 2 images, average the red values together, average the green values together, average the blue values together, call it a day, and go home. Okay? YYPP, CW green, / red, dot n, CW blue, dot, / red, dot in dot. There we go. So the red value at each pixel is set to the average of the original red pixel and vector 2's red pixel value. That's it. That's the whole thing. And so we're going to need to take in another parameter. I have to undo all this. So image 1, image 2. If arg c equals greater than 2, and image 2 dot open. Is that not it? Dot load. JPEG. It works. I don't know. I don't know how it works. All right. So image to vec. So we need another vector. Okay, so now we're going to do filter 3. Okay, here we go. So we're going to pass in vec and vec2 like this. Filter 3 needs to have its prototype changed. We change that. Y shift 4, P to paste, and comma and 2. Okay, make error expecting something, line 127, shift 2. That's a good idea. Make any questions about what I just did there? I went kind of fast. We're kind of out of time. So I'm having it take a second image as a parameter, and we'll see how well this works first time. But you can use this to like add a watermark, because that's one of one of your tasks. So if we go a.out away as the original image, and we will composite honor.png on top of it. It didn't crash. That's a good sign. We'll come into here, and we will open up filter 1, and we can see we have brightened away. Open up filter 2. We can see we have vignetted it. Open up filter 3, and we got nothing. No, wait. I opened up the source code, not the JPEG. Did it not save? Ooh. Oh, it's called output 3? Filter 3. Come on. Who wrote this code? Filter 3.jpg. Okay. Okay, any questions about this? Refresh the directory, and output 3. Ew, that didn't work. Yeah, I'm gonna upload both lectures. Oh, that was unexpected. All right, filter3.cc. Let's see if we can figure out what's going on here. So, number of rows should be set to the minimum. Debug that, I guess. Let's see here. Rows, columns. It's not going out of bounds, or that would have thrown. Let's just try this. Yep. Let's just try this. We'll just try setting the value of vector 1 equal to the value of vector 2 there, so it should just overwrite the first image with the second image, which is actually all you really need to do when you're watermarking, right? You just plop the second image on top rather than trying to blend it in, and then maybe we'll figure out what I did wrong. So we'll see if this works, because it might not be. It might, you know, it's probably the load, isn't it? Yeah. So I don't remember how to load using that. All right. a.out, away, and honor. Oh, it's a PNG file. That's why. No wonder it didn't work. Okay. Just a load? Oh, there is. Okay, well, that's simple. Okay. Use load instead of load JPEG. Yeah, thanks, Hazelton. Perfect timing on that one. Yeah. Yeah, so by loading a JPEG when it was a PNG format, naturally you get hot mess out of it. Okay, here we go. This should work. I'm feeling confident now. I'm feeling confident about this. Honor.png. No crashes. That's always a good sign. Let's remove output 3. Refresh over here, and we'll see honor output goes away, but filter 3 is now there. Open it up. Ew! So that's what's loading in the second one. Looks cool now. Let's see here. Columns. Yeah, okay. That's why. Okay. Because I have a global variable that holds how many rows and columns are. And that's assuming there's only one image. So if we have a second image and we need to make an int calls 2, and so that equal to image 2 dot width and rows 2 dot height and stride. Does it use calls there? These are globals. Image. Oh, it's because image to vector. Ah. Yeah, that's why you shouldn't use globals, people. That's why you shouldn't use globals. It's terrible. Don't use it. Don't use it. Just going to pass them in here. Int calls, int rows. There we go. And then here we will pass in int calls, int rows. Columns first, then rows? Okay. Dubious. Okay. Oh, that's why it's backwards. Yeah, that should be row. No wonder it's backwards. Yeah, okay. All right, okay. Oh, it's because that's a CImage format. The CImage format holds it in. Oh, okay, that's so weird. Okay. Okay, so you need to become an int. You need to become an int. You need to become an int. Is stride used anywhere? Yeah, it needs stride passed in as well. Probably not. Int stride is equal to last times rows. And Same for you. This is why you shouldn't use globals, people. Who wrote this code? delete you, not globals anymore. Okay. Image to vec, image vec calls rows, rows 2. Vector to image doesn't require that, I guess. Maybe it does. Well, after all that, probably should have backed up the file. Huh? might have to copy it out of the students directory. Better doing that. So are we going to be modifying mandate this watermark of the square? No, you don't have to. So in like I said, if you look at the previous lecture, I go over this. I'll post both of these because I did kind of go over different material today. I made a function that takes in the image and then does a for loop over a rectangular chunk of the image and sets all those points to black. And so you can do, like, so this thing here is going to make a vertical stripe of black. And then this one here makes a vertical stripe of black. And so by doing 2 of those and 2 horizontal ones and 2 vertical ones, then you get a hashtag and so on and so forth. So you can just directly write to the image and make your little watermark. Okay. So you don't have to do this. Okay, let's just see if I've completely broken it or not. Dewey and honor, and let's see what we got now. Like, did even the first one break? It's possible. Nope. So that's all working still. That's good. That's good. All right. Filter 3, moment of truth. There it is. There's what the problem was that I had a global variable, which you should not do. And it was that way due to legacy reasons, really. There was a global variable that held the number of rows and the number of columns in the image. And so when I had a second image, all the functions for accessing the image used the other images, rows and columns. And so if you guys remember the row major ordering formula, or like to map between a 3D array and a 1D array, you take this times this plus this. It was using the dimensions for the wrong image. And so that's why we got this, scattered look, because it was just wrong. It's just wrong. Okay, so now we just need to composite it instead of replacing it. So we'll just switch this back here and hit make, run, and let's look at our filter 3, and there we go. It's like that Vietnam meme, where like the dog is staring off into space and there's like Vietnam helicopters and stuff like that behind it. That worked out surprisingly brilliantly. That I don't know what to say. I don't know what to say. This is you'd give me a C on this one? Yeah, that's fair. This overexposed knuckles here in the middle here, because it's brightened twice. This is 4 times the brightness in the center, dipping out to 0 brightness on the corners. Just makes them look extra dopey with the rainbow pattern on, and then just the ghost of a trillion dead in the background there. That is a thing. All right, I'm gonna save this one here, and I'm gonna send that to Kurt I'm gonna ask. Kurt's the photography teacher on campus, and I'll send that to him and ask him to rate my contribution to world culture. So what I'll do is I'll put a copy of all of this code up into the public directory. So then, let's see if I have any Vim public image processing image. No, there isn't one. Okay, Maker public image processing, and I'll just copy all of the files up into there. And so here you go. So all the demo code that I've done today, that's all up in there. And you can, yeah, that's the one. That's the one. Yeah, the dog that's staring at the Vietnam. Yeah. So obviously you can't just turn my code back into me, but there should be enough demo code in there for you to kind of see things and look at them. On Friday, we're just going to be doing a Halloween party. We'll have some lab time. You can ask questions and stuff. And basically, we're just going to come in, have fun on Friday, do a little Jackbox or something together, and yeah, it'll be fun. So this is a fun assignment. I hope you guys can see that you just kind of do whatever and just see what works, see what looks good. Try to match the image to the code and come up with something cool. Okay. So technical difficulty, artistic. All of you have been given partners if you didn't ask for one, and so message them on Canvas and get set up and start working on it. Okay. So I hope you guys had fun today. I did. This is one of my greatest. One of the greatest things I've ever made. So I'll see you guys. On Friday. Right, peace out.